Alright, in the previous lecture, we proved the theorem saying that in any three-connected graph, we can find an edge whose contractions make a three-connected graph, unless graph is too small. So today, we're gonna prove a variation of that, where we wanna keep additional property, the graph is simple. So here's the theorem due to Tutte, and it's commonly called Tutte's wheel theorem. Which states as follows: if G is a simple three-connected graph, then it has an edge E such that G delete E or G contract E is simple three-connected. Unless. So there are examples where this doesn't work. But what are the examples? So here's one example. So this is called the W5. So it's a wheel. So you start with the cycle of length 5 and add one vertex adjacent to everybody. Then basically you have two kinds of minors. So if I contract this edge or that edge, if I contract an edge on the rim, then when you end up is this graph, right? So G contract E, and this graph is not simple, but it is three connected. How about G delete E? If I delete E, then you end up with this graph. It is simple, but not three connected, right? Because I can delete these two vertices and graph stays graph become disconnected. How about F? If I contract F, then again I have yes, this is the G contract F, and it's not simple. It's not three connected. How about deleting E? Deleting F? This is simple, but not three connected, because I can delete these two vertices. Right. So this is one example where this wheel theorem fails, right? You cannot reduce by a single edge reduction, like a deletion and contractions, while keeping simple three connectedness. And the Tutte's wheel theorem says that this is the only counterexample, so it's isomorphic to the Wm for some. Okay, so what is Wn? Cn plus one vertex. So Cn is the cycle of length n, one vertex adjacent to all other vertices. Alright, so that's the Tutte's wheel theorem. So this lecture will be a proof of that. Okay. So how do we prove this theorem? We start with this previous theorem about the contractions. Let me talk about strategies, right? So I knew, right? We know already that there is an edge. So there is an edge E such that G contract E is 3 connected. Why? Because of this previous theorem. And then, oh, by the way, oh yeah, I mean, I don't have to worry about that. I mean, if the graph is too small, like if it has only 4 vertices, and then it's just a matter of case checking. There are now not many graphs, right? But if I have 4 vertices, then graph must be, if number of vertices is 4, then G is equal to isomorphic to K4. And K4 is isomorphic to W3. So nothing to do, right? Because W3 is one of the instances where we say it will fail. All right, so that's why we can assume that graph G has at least 5 vertices, and therefore there exists an edge whose contractions make a 3-connected graph. But that means we can assume that this graph is not simple. Okay, I mean, I can start by saying, suppose that G contract E. Yeah, so neither G contract E nor G delete E is a simple 3-connected for all edges E, right? So that means G contract E is not simple. So when you contract an edge, how is it possible that this contraction leads to a not simple graph? Well, the only reason is it is in a triangle, right? So you have a triangle. When you contract, you make 2 parallel edges. That's why you have a graph which is not simple. Okay, so that means initially G had a triangle cycle of length 3 containing E. So I choose an F like this. So let's say F is on another edge in the triangle. Now let's try to delete F. Now G delete F is simple. So G delete F is not 3-connected by the assumption, because there's no edge which gives you a simple 3-connected graph by deletions. Alright, so G delete F is not 3-connected. How is it possible? Well, you have a set of size at most 2, and after deleting, there's no edges from left to right, and the edge F is over here. Okay, now what does that mean? Where is E? Where is E? Well, this red edge is F joining left to the right, and there used to be a triangle here, and there must be a triangle, but the only way you can make a triangle is like this. So E is one of those 2 edges, so let's say this is E. Okay, so then what does that mean? That means I can find the, yes, right. So that means I can find these, oops, yeah, this vertex. Yes. So I'm hoping to find another edge which I can contract. Oh, I see. Now, I know that G contract E is 3 connected. So how is it possible? How is this possible? Well, if I had any vertex here, if this has any vertex, then after contracting E, it may look like this, right? This is F. Now, when you delete these two vertices in G contract E, graph looks like disconnected. That's weird because we said that the G contract E is 3 connected. How is this possible? Well, the only way it's possible is to make this part to be empty. So there's no other, but there is only one vertex. Okay, so that means graph is actually like this. So you have a one vertex F, no, one vertex, and then here's a E, right? Huh. Okay, and then let's choose this edge. Right. So this is the beginning of the proof. Okay, so we end up with, start with E and I have an edge, and then I can find another edge here, and this vertex will have degree 3. Right, because there's no neighbors of this guy other than these 3 vertices. And it has the degree at least 3 because graph is 3 connected. So therefore, its neighbor looks like this. Now this is good. This is good. Now let's look at the next edge. So let's say this is E1. So what happens if I contract E1? If I contract E1, right, look at this picture. If I contract E, I knew the graph is 3 connected. But these two edges become parallel, right? If I contract E1, I may add this new edge, but other than that, it looks same, right? So since G contract E is 3 connected, G contract E1 will be 3 connected. Right, so let me draw again. So here's 2 vertices. They are gonna. So in G contract E, it looks like this. And what about G contract E? G contract E1. E become an edge here, and this is an edge, right? This is, but the connectedness has nothing to do with the simpleness. So I can, if I ignore this edge, then everything here, all the edges here are present here. Okay, and it may have more edges. So if this is 3 connected, that's 3 connected. So we know that G contract E1 is 3 connected. So it's not simple. Alright. So this is E. Okay, so EF and E1. Now, again, now you feel, this looks like repeated, because how is this not simple? Well, that's not simple because you have a triangle. Where is a triangle? You have two cases. Maybe it looks like this, or it looks like that. One of these two. Because the vertex, this vertex is degree 3, you only have two options to be parallel. I mean, to make a triangle. So either this is triangle, that's here, or that is triangle. Okay, and there's actually a symmetry, some symmetry that, I mean, I wouldn't later, I will not care, but I will not care about this edge. I will only care about this vertex. This vertex is adjacent to all three. This vertex is adjacent to all three. So what I will care is that the last edge, the E1, is an edge that whose contraction is 3 connected. So let me focus on this configuration, because in this configuration I'm gonna swap these two edges. So we may assume by swapping E and F, I will tell you why this is okay, because I'm gonna define precisely what kind of substructure we're gonna construct by this proof. Now, it's not simple, so we have this. So let's say this is F1. In this case, that's F1. All right, now we look at the G, delete F1, then it's a simple. So it's not reconnected. What does that mean? That means I have an F1 and two vertices, and most two vertices, and right? So this triangle must be, yeah, so this blue triangle is somewhere here. So F1 and F and E1. And again, by contracting E1, we must have a 3 connected graph, so therefore this side is empty. This is the only vertex. And then contracting E1 is same as contracting E2, which is this edge. I mean, except contracting E2 will make more edges, right? I mean, this vertex will be adjacent to that vertex after contracting E2, which could, I mean, these two could be non-adjacent in G, but after contracting E2, not adjacent in G contract E1, but after G in G contract E2 could be adjacent. But other than that, all the adjacencies are same. So by the same logic, we deduce that G contract E2 is not, oh no, is 3 connected. but not simple. So what does that mean? That means we're gonna end up with this kind of graph, right? E1, E2, and if you're lucky, if we keep doing this, we end up with this, which is a wheel. If you're not lucky, in this case, we may continue. Right? But since graph is finite, eventually you end up with this. With the property that all these vertices have degree 3. So that's the beginning of the proof, and that's how we're gonna prove. Okay? I didn't say the proof yet. So this is the structure of the proof. So how do we prove it more precisely? Okay, to prove, we define a structure called K-fan. As a path, so x0, e0, x1, e1, x2, e2, ek, xk, with a vertex c other than different from x0, x1 up to xk, adjacent to all vertices on the path. So meaning x0, x1, xk. So what is K-fan? So you have a path like this. Oh, but I didn't finish the proof. Definitions. And such that, so I have extra conditions. All internal vertices of the path have degree precisely 3 in G. So all these vertices have degree exactly 3 in G, and when you contract the last edge, it's 3 connected. Okay, so that's the definition of K-fan. And we assume that graph doesn't have any edge, so neither G contract E nor G delete E is 3 connected for all E. Then the first claim is G has a 1 fan. Why? Why? We have seen it. There is an edge. Edge E such that G contract E is 3 connected. So that means there is a triangle having E, because G contract E is not simple. and that's enough, right? So you have an edge E, and when you contract, it's not it is three connected if when you contract E, and graph is I mean that's the definition of one fan. So that's okay. Now what we do is we choose a maximum K such that a K fan exists in G. So that E x0, E0, x1, EK, xk with C be the K fan in G. I should say a K fan. Yes. Because graph is finite, there is a maximum number K such that graph has a K fan. Now let's look at the last edge. Right. So here's a C, here's the xk. So since G delete cxk is simple, G delete cxk is not three connected, right? So there is a set x of size at most 2 such that G delete cx k delete x is disconnected, right? So here's an x, and when you delete cxk, this edge graph is disconnected. Since G delete x is connected because graph is three connected, C and xk are in distinct components. Of G delete cxk delete x. So that's this picture, right? We've seen it already. So this is C, this is xk. All right. Now they are in a triangle. They are in a So that means x must contain xk minus 1 because it's a triangle. Because you have a triangle, and the only way you can have a common neighbor is to have somebody in the middle. Now we know that G contract xk minus 1 xk is three connected. Right? Because that's the definition of K-fan. The definition of it's on the left hand side. Definition of K-fan states that when you contract the last edge, you have to have a three connected graphs. All right. So that means the component of G delete cxk delete x containing xk has no other vertices. Right? So this component, this is the only vertex in this component. Now, since xk has degree n is 3, because graph is 3 connected, every vertex has degree n is 3. Xk size of x is 2, and xk is adjacent to all vertices in x, and degree of xk is 3, right? Okay. So let's call this vertex to be xk plus 1. Vertex of x other than not equal to xk minus 1. So that's gonna be xk plus 1. All right. So let's assume one case. Suppose xk plus 1 is not equal to x0. If this is the case, then we claim that G contract xk plus 1 is 3 connected. Oh, but actually we have seen it already, right? Just compare G contract xk minus 1 and G contract xk plus 1. If two vertices are adjacent in G contract xk minus 1, then they are adjacent in G contract xk plus 1, right? And you might have one more edge, C to xk plus 1, but other than that, everything looks same. I mean, except after you ignore the parallel edges. So therefore, G contract xk plus 1 is 3 connected. But what does that mean? That means it's not simple. So there is a triangle containing xk plus 1. So where is this triangle? Now xk plus 1 has only 2 neighbors. No, xk has only 2 neighbors. So this triangle is either xk and xk plus 1 and xk minus 1. That's one possibility. Or xk plus 1 and c. So if this is the case, if the second case, so xk plus 1 is adjacent to c, then what we end up is this becomes xk plus 1. How do I know that the xk plus 1 is not equal to any of these vertices? Well, I know because I knew by assumption that this is different from x0, right? But how about x1? Well, xk is not adjacent to x0. Is it clear? Right? Because neighbors of xk's are only these three vertices. So that means, yeah, then, and I know that all these, I know that all these vertices are distinct, right? And xk is not adjacent to any of these, so therefore xk plus 1 is not equal to any of them, right? Xk has degree 3, so yeah, so indeed this is a pass. So that means this is become k plus 1 fan. Why? Because this, when you contract this edge, it's reconnected. But that's contradiction, because we assume the graph doesn't have when you choose k, that was chosen to maximize k so that there exists a k fan. So that's contradiction. The graph doesn't have a k plus 1 fan. How about the first case? If 1, so xk plus 1 is adjacent to xk minus 1. How is this possible? Okay, and if k is bigger than 1, then I knew that the only neighbor of this vertex is xk minus 2. And also I know that xk, okay, yeah, right. I knew that if k is at least 2, then degree of xk minus 1 was 3. So these 3 are all the neighbors of xk minus 1, which means that xk minus 1 is equal to xk minus 2, which is impossible. Contradiction. Why? Because xk is not adjacent to xk minus 2. So if k is at least 2, then this is contradiction. If k is 1, then x1 and x2, this is adjacent. And I know that this is the edge that I can contract and make 3 connected. In this case, I can find the 2 fan again. Now let's put different names. So this is my C, this is my new x01, x0 prime, x1 prime, x2 prime, C prime. And when you contract, this is 2 fan. So that's contradiction. K was chosen to be the maximum that there exists K fan. Alright, so what did we do? We proved that xk plus 1 is equal to 0. Okay, so here x0, x1, xk minus 1, and this is equal to xk plus 1, and c is adjacent to everybody. So are we done? No, we are not yet done, because we have to show that this is the whole graph. But I have a very nice information that all these vertices have degree 3. Okay, so if G has a vertex V other than x0, x1 up to xk and c, then G delete x0 delete c is disconnected. Because x1, x2, xk have degree 3, right? So these vertices have no other neighbors except these people. Like this vertex has neighbor only these 3. So when you delete these 2 vertices, graph could be disconnected if I have a vertex outside. Oops. Yes. Yeah. So that's contradiction to the assumption that graph is reconnected. So G is isomorphic to WK. That's it. That is the proof. Okay. So this proof says that any count example for the Tutte wheel theorem is actually the wheel, isomorphic to the wheel. So how do we use this to do something useful? So imagine that you have a statement. Let's say you want to prove something for simple 3-connected graph. And one way to prove it is by induction on number of edges. And you assume that graph is simple 3-connected. Now by using Tutte wheel theorem, I can always find an edge whose deletion or contraction is simply 3-connected. And then once you reduce, then you can apply induction hypothesis and say something is true for G delete E or G contract E. And then try to go back by adding an edge or uncontracting an edge. So that's very useful. What's the other situations? So for instance, I want to construct all simple 3-connected graphs. Imagine that I wanna generate all 10 vertex 3-connected graphs. What should I do? Up to isomorphism. So I don't want to generate same thing twice, but okay. So how to generate all simple 3-connected graphs where on 4 vertices there's this unique graph, right? There's only one. What about 5 vertices? Tutte wheel theorem says that any 5 vertex simple 3-connected graph is built from a smaller simple 3-connected graph by adding an edge or deleting or contracting. I mean uncontracting a vertex, right? So if I uncontract from W3, then what we end up what do we end up? How do we this is every vertex has degree 4, so you never get it as a contraction of something. So the only 5 vertex graph is nothing. So this is W5. And then you add an edge. Oh, I see. Actually, I should have a... Okay. It has to... It is actually better to state in terms of a number of edges. 1, 2, 3, 4, 5, 6. 6 edges. And 7 edges. There's no simple trigonometric graph on 7 edges because you cannot add an edge. You cannot... there's no way to add an edge, no way to uncontract, right? How about 8 edges? Then you have W4 and nothing else. Huh. How about 9 edges? You add again, this is the only 9-edge symmetrically connected graph. There's no other choice. What about 10 edges? Now we are seeing more than one example. So K4, right? By adding one more diagonal, or you have a W5, right? Because all simple trigonometric graphs can be built from some wheel by adding edges and uncontracting repeatedly, right? So if I know the list of simple trigonometric graphs on 9 edges, I can build a list of simple trigonometric graphs on 10 edges just by going through each list, each member of the list, and adding one edge, or uncontracting someplace, or oh yeah, I should have uncontracted. So there's a cheating. Right. What happens if I uncontract from here? I have this graph, or I have right. So there are three 9-edge symmetrically connected graphs. These vertices have degree 3, so there's no way to uncontract. So I have more graphs on 10 edges. Right? So first going through these 3 graphs and adding an edge. So like a K4. Oh, yeah, now it's becoming painful because I have to add all possible edges like this. Oh, up to symmetry, that's it? Yeah, there's no other. Right, that's the only one coming from here. How about that? Oops. Oh, something's wrong. Yeah. Yes. So in this case, I could add an edge like this, and there may be more, right? And then W5, and then uncontract, and then not only adding an edge but also uncontract. This graph, oops, all these vertices have degree 3, so there's no way to uncontract. These have degree 3, no way to uncontract. So the only place you can uncontract is here or there or this vertex. So for instance, I might have oh, but actually it's the same as this guy. Okay, so all right. So kind of these tedious jobs can be done more efficiently by using computers. So there's a software called the Tutte that detect the isomorphic graphs, and that's quite nice. So once you use that, you can generate graphs without isomorphisms. Anyway, so that's one way, one applications. You can, when you want to generate all simply connected graphs on 10 edges. If you have a list of all simply connected graphs on 9 edges, you can generate 10 edge graphs by certain rules, right? Now, there's a, sometimes this is called a chain theorem. Why? Because this is a corollary. For every simple tree connected graph G, there is a sequence G0, G1, G2, Gn of graphs. Okay, each of them is a simple three connected graphs such that G0 is isomorphic to a real graph, and Gi is equal to Gi plus 1 delete E or contract E for some E, and Gn is equal to G. Alright, so from any simple tree connected graph, I can find the long chain of graphs, simple tree connected graphs, that when you go down, you only do the contraction or deletions, and you can keep the simple tree connectedness throughout the all stages. So that's why this is sometimes called a chain theorem. All right. Now, you may wonder what happens if I have a different target. So for instance, I have a graph G. Tutte's wheel theorem says that I can reduce, and I always end up with a sum wheel where all these graphs are simple tree connected. So the question is, can I make a different target? So imagine that my graph G contains certain minor h. I know that G contains h as a minor. Can I then find some chain where each step is by deleting one edge or contracting one edge? Can I find such a sequence of simple three connected graphs towards a different target. So there's such a theorem. So let me state the theorem without the proof. So usually I teach this theorem for matroid course, but not in the graph theory course. This is called this is due to Simmer. Who was my PhD advisor. It's commonly called the split theorem. So let HG be simple three connected graph. And let me tell you, there are exceptions, so, but anyway, let me state the consequence, or what we want. If H is a minor of G, then there is a sequence G0, G1, Gn of simple three connected graphs such that Gn is equal to G and G0 is, now I cannot say equality here. I'm isomorphic to H, it's not equal, and Gi is equal to Gi plus 1 delete E or Gi plus 1 contract E for some H E of Gi plus 1, unless let me just say that unless H is a real graph. Okay, no, unless okay, there's a better. Okay, if H assuming that if H is real graph, oh, okay. If H is a real graph, then I want it to be the largest real minor, but let's not worry about that. So unless H is real graph. If H is real graph and if it's the largest real minor, then if it's the largest real minor, then it's true. So, and there is a real, if G, okay, if and G has a real minor larger than H. So that's precise statement. All right. So this is a analog, or extension of Tutte's wheel theorem for general graphs. Right. So in a chain theorem, Tutte's wheel theorem, you can always end up with a wheel, but you cannot set the target to be any minor. So in a split theorem of Simmer, you can set the target, and then you can still go by one, unless the target is a wheel graph and it's not the largest wheel minor. Otherwise, you can always do that. Okay, so that's it for 3 connected graphs. And in the next lecture, we will start on planar graphs. Thank you.